Okay, for question number 3, I'm going to encourage you to write small because there's a lot to do with this. So if you can kind of cut the space in half, top to bottom of what's left for part A and B. So we're going to calculate the pH of a 0.2 molar NH3 slash 0.1 molar NH4 buffer. So you'll see the concentrations of these are not the same, so they don't always have to have the same concentration. So we're going to start with just kind of looking at what we have. We have 0.20 molar of this, and we have 0.10 molar of this. Now what makes this different is this is a Kb, and remember our equation is pH equals the pKa plus the log of the base over the acid. So I've got to get this to be a Ka value instead of a Kb value. So this goes back to that Ka times Kb equals Kw. So to get Ka, I'm going to do 1.0 times 10 to the minus 14th over my Kb, which is 1.8 times 10 to the negative 5th. Okay. And that's going to give me 5.6 times 10 to the negative 10th. And if I take the negative log of that, that's going to give me a pKa value of 9.26. So when I plug all of that in, I'm going to have my pH equal to 9.26 plus the log of the base, which is the NH3, the log of 0.2 molar over 0.1 molar. And when I solve that, I get 9.58. Okay. Now, notice this is higher than the 9.26 that we would predict, but again, there's more base than there is acid, so that makes it a little bit higher than what we would expect. Okay. So for part B, we want to know the pH of this buffer after we add 10 milliliters of a 0.1 molar HCl solution to 65 milliliters of the buffer. So those are all important numbers. So the first thing we have to look at is stoichiometry. So what is HCl going to react with? Again, strong acid is going to react with the base part of that. So it's going to be NH3 plus the H3O from the HCl, and that's going to create more NH4. So I'm going to look at this from a stoichiometry perspective first. So I know I have 0.2 molar of this times 65. And instead of converting that to liters, I'm just going to make that millimoles. So when I multiply that together, I'm going to get 13 millimoles. Okay. My H plus is going to be 10 times 0.1. Molar, and that is going to give me a a value of 1 millimole. And then my NH4 was 0.1 molar times 65. That's going to give me 6.5 millimoles. So my reaction is going to be limiting with this. So I'm going to subtract 1 millimole because that's all I'm going to have available to me. So that's going to give me 12 millimoles of this. I'm going to use up all of my acid, the strong acid. I'm going to zero that, and I'm going to add 1 millimole to this to get 7.5 millimoles. So key idea here is stoic is in moles. Okay. And equilibrium is molarity. So now I'm back to looking at it from an equilibrium perspective. So if I go back into the equilibrium of my equation, I have remaining 12 millimoles of NH3. Now my new volume is going to be 10 milliliters plus the 65 of the original. So I'm going to have divided by 75 milliliters for a concentration of 0.16. And over here, I'm going to have 7.5 divided by 75 for a concentration of 0.1 molar. So when I substitute back into my pH equation, my pH is still going to be 9.26, my pKa value, plus the log of the base, which is the 0.16, over 0.1. And when I calculate all of that, I get 9.46. And again, that makes sense because our original pH for part A was 9.58. We added acid to it, so the pH should go down.